In this PowerPoint, we're going to talk about torque and equilibrium. So here we have an object. This is a door that has a pivot point, and this door has a force that's being applied, and that force is being applied at a certain distance away from the pivot point. So we have the force being applied, and then we have the pivot point here, and then that distance is going to be the radius, usually referred to as the radius, because when we got something that has a pivot point, it's going to be rotating. So that force is being applied at a distance from the pivot point, and then there's an angle between that door and the force, which means there's an angle between the displacement from the pivot point and the force itself. So a torque is a turning or a twisting effect due to a force, and it's usually found by the product of the force and the perpendicular distance from the pivot point. So if we look at this this force right here, here's the distance that the force is being applied, but the perpendicular distance is going to be this part right here. So if we go from the pivot point straight to the force, that shortest distance, that's going to be the perpendicular distance. Now, a torque can cause a change in rotation, so it can actually accelerate an object that's rotating, or in some examples it can decelerate, so it can slow it down from rotating, or it can speed it up from rotating. So here are some examples of some torques and some different types of torques applied to a door. So if we take a torque, it's going to be equal to the force times the distance from the pivot point times sine of theta. And this part right here, that is the lever arm. So r sine of theta is referred to as the lever arm. That also gives you the distance, the shortest distance from the pivot point to the force itself. All right, so some examples. We have a bolt on a car engine that needs to be tightened with a torque of 35 Newton meters. You use a 25 centimeter long wrench and pull at the end of the wrench at an angle of 60 degrees from the perpendicular. How long is the lever arm, and how much force do you have to exert? So the lever arm is going to be r sine of theta. So we have r, which is 25 centimeters times sine of 60 degrees, and that gives us 21.7 centimeters, which is 0.217 meters in base units. In order to find the force, we take torque. That's going to be equal to the force times the lever arm. To find the force, we divide both sides by the lever arm. So we take the torque of 35 divided by 0.217. That gives us a total force of 162 newtons. Alright, so objects in equilibrium. There are two conditions of equilibrium. The first one we already know. We said the net force is going to be equal to 0. That means that any upward force and downward force are going to be balanced, so they're going to be equal to each other. It also means any forces to the left and any forces to the right are going to be balanced as well. That one we know, but we also, so we don't want objects to accelerate, but we also don't want objects to rotate. So the second condition of equilibrium is that the net torque is equal to 0. So the force times displacement from the pivot point is going to be, all those torques are going to be equal to 0. Now that means that we have counterclockwise torques and clockwise torques, so we have to define directions with those. Counterclockwise is going to be positive, clockwise is going to be negative. If you do anything with the unit circle, as you start from the from the positive x-axis and you go counterclockwise, that's the positive direction. So physics uses that as well. The counterclockwise direction is going to be positive. So let's say we got this object right here that's being balanced. We got a 500 gram mass over here on the left, and we got a 600 gram mass over here on the right. And then we got the fulcrum right in the middle, which fulcrum is what's going to be identified as a pivot point. It doesn't have to be the pivot point, but a lot of times we make the fulcrum the pivot point just because it's pretty convenient, and that's what it's going to rotate around. The reason we don't have to make the fulcrum the pivot point, because if we want something in equilibrium, then we can set the pivot point anywhere we want, because we don't want it to rotate around any pivot point, much less the fulcrum. So we say the 500 grams is 51 centimeters from the fulcrum, and then the 600 grams, we don't know how far that is. We need to figure that out. So in the diagram to the right, how much force is the fulcrum pushing up with? Well, that's pretty easy. We take the force that the fulcrum is pushing up with, and we got the force of gravity from the two objects that are pulling down. So that means that the upward force and the downward force has to be balanced since it's in equilibrium. So the upward force is force 1. We call that the force of the fulcrum. Then we got force of gravity 1, which is the mass right here, and then force of gravity 2 over here. So we go ahead and plug that in. 0.5 times 9.8 plus 0.6 times 9.8. The 600 and 500 grams need to be converted to kilograms. And then we get to the force of the force on the fulcrum is going to be 10.78 newtons. So what's R2? What's the distance of the 600 gram mass from the fulcrum? We're assuming, by the way, that this bar right here, whatever this is already balanced, or it has no effect on the torque of the system. There are some times when it does have a torque on the system, and that's when the fulcrum is not at the center of balance of whatever that is. So what is the distance of the 600 gram mass? Well, we're going to use the torque, where the torque clockwise and the torque counterclockwise are going to be equal to each other. That means that we're going to have a mass 1 is going to cause a rotation this way, which is going to be a counterclockwise rotation, and then mass 2 is going to cause a rotation around the pivot point. It's going to cause a rotation this way, which is a clockwise rotation. So that makes mass 1 a positive torque, and mass 2 is going to cause a negative torque. So we go ahead and plug that in. Force of gravity 1 times radius 1 is going to be equal to force of gravity 2 times radius 2. We go ahead and plug in the numbers we know, and then solve for R2, and we find that R2 is going to be 42.5 centimeters. Now that's one way to do it. If we set our pivot point where the fulcrum is, then that's going to be the distance of 42 centimeters. But what if we don't want to set that as our pivot point? What if I want to change the pivot point? It should hold true that no matter what pivot point I choose, that I'm going to have no rotation around any of those pivot points. So it's convenient to place our pivot point here and say that our rotation is going to be 0 around this, but I can place that pivot point wherever I want because I don't want it rotating around any point anywhere. So I can actually move that pivot point to wherever I want as long as I say that there's no rotation around that point, or no change in rotation around that point. So if let's suppose that we can choose a pivot point here instead. So now we got a pivot point on this end, and we have the force from the fulcrum that's going to be causing a torque, and then we have the force of gravity from the 600 gram mass that's going to be causing a torque also. Let's see if we can go ahead and figure out this R2. Now the lever arms are going to change because the distance of this force is going to be R1, but the distance between the pivot point and mass 2 is now going to be R1 plus R2. So the lever arms have to change, as well as the what we consider clockwise and counterclockwise according to this new pivot point. So we take the torque of the clockwise rotations and the counterclockwise rotations. We're going to set those equal to each other. And you can see that this the fulcrum is actually going to apply an upward force, and that's a counterclockwise torque around the pivot point. The 600 gram mass has a clockwise torque. So we got the 600 gram mass trying to rotate it clockwise, and the fulcrum trying to rotate it counterclockwise with respect to this this pivot point right here. Now if you notice, the 500 gram mass, that force of gravity is applied at the pivot point. And since it's applied at the pivot point, then that means the force that's applying is not going to apply any torque, because the radial arm between the pivot point and the force that is going to be 0. Alright, so we go ahead and plug in our numbers. We got the fulcrum, which is force 1. That's going to apply a torque that multiplied by the radius 1, or the lever arm 1 here, and that's going to be equal to the force of gravity of 2, the 600 gram mass, and that's going to be multiplied by the radial arm, which is going to be R1 plus R2, the total distance from the pivot point. So we go ahead and plug in our numbers. We got 10.78 times 0.51, and that's going to be equal to 0.6 times 9.8 times the summation of 0.51 and whatever radial arm 2 is going to be. Alright, so we calculate this out. We divide both sides by 0.588, and then we go ahead and subtract both sides with 0.51, and we find that the lever arm, the radius 2, is going to be 0.425, which is the exact same answer as what we got before. So basically this shows that it doesn't matter where we place our pivot point, as long as we're consistent with the clockwise and counterclockwise rotations, as well as the new lever arms, then we'll still get the same answer regardless of how we do it. Alright, another example says Carl has a mass of 43 kilograms and sits 1.8 meters from the center of the seesaw. Steve, whose mass is 52 kilograms, wants to balance Carl. How far from the center of the seesaw should Steve sit? So we got this balance, and we're going to have a clockwise torque and a counterclockwise torque. And I really don't know who's going to cause a clockwise and counterclockwise, but I know on a seesaw each one's on either end, so one's going to cause a positive torque, the other's going to cause a negative torque. So we got one on one side, one on the other. So force of gravity 1 times radius 1 is going to be equal to force of gravity 2 times radius 2. That's 43 times 9.8 times 1.8. That's going to be equal to 52 times 9.8 times R2. And then we divide both sides by 509.6, and we find that R2 is going to be 1.49 meters. Now, hopefully that kind of makes sense with 1.49 meters for R2, which is where Steve is sitting. Steve has more mass than Carl. With more mass, then he needs a smaller lever arm, so 1.49 as opposed to 1.8. And that's kind of the trade-off in order to balance. With more force being applied, he's going to have a smaller lever arm, so that way when they multiply together, they get the same answer.